Hello and welcome to subfactors. So today we'll have a more relaxed lecture about, it's going to be only about subfactors of integer index. So I'll try to unify this for construction. We've seen the last time we was in quantum groups, so it's not going to be very complicated. So let's find this presentation. Group actions and fixed points of factors. So it's going to be somehow quantum algebra in the usual sense, not very complicated. So we've seen last time for basic example of subfactors. So first we have the cross products by finite groups. So you take a one factor, then you need a finite group G acting on it, you form the cross product. And in order for this cross product to be a factor 2, the action must be minimal in the sense that the commutant of the fixed points must be trivial. Then you obtain a subfactor, of course, of index n, and being the order of the group, you enlarge somehow by n things. And this is called usually either cross product subfactor or other depth 2 subfactor, because we'll talk later about depths. These are depth 2 subfactors. So that's the terminology which is used by everyone. Now another example, this time using fixed points instead of cross products, is given by subfactors like this, Pg in pH. So you need to take, it goes in the other sense, you need to take a subgroup H of a group G, and you can take them compact. I mean, no need for them to be taken finite. As long as the index is finite, let's call it n, this is going to be a subfactor of index n. Once again, the only assumption is the minimality of the action of G for getting one factors. So what we have so far, we have cross products, index n integer can be anything, and subgroup subfactors also of index n integer can be anything a priori. Now we have two more constructions, this time of index square of an integer. So first is the Wassermann subfactor, once again G compact acting minimally on P. And then you take a projective unitary representation of G, meaning that's the same as an action on the n by n matrices. So then you can form this subfactor. And this has index n squared because the dimension of Mn of C, what you enlarge by is n squared. So this is the Wassermann subfactor. And finally, there is something which is a bit dual to the Wassermann subfactor. So instead of taking a compact group, we take a discrete group. And instead of a minimal action, we assume that it has an outer action. Outer meaning that the commutant inside the cross product is C. It's really dual somehow to the previous one. We'll see later. And now the other piece of data, instead of projective representation, you just take some generators for your group. And what you can do, you take Q as diagonal matrices inside the Mn of Q, but the diagonal matrices are twisted by the generators G on GQ. So this is once again, index n squared is called diagonal subfactor because it appears diagonally. Now, the claim is that all these things are of the same nature. I mean, you can basically see, if you look at this, what we have groups, of course, of all types, and then fixed points or cross products. But the cross products are also fixed points or vice versa. So definitely this can be unified. And the best way of doing it is as follows. So let's, here I wrote again the subfactors. So depth 2, subgroup, Wassermann, and the diagonal. And we can write them using this form. So finally, in this form, A0 tensor P fixed point by G, included into A1 tensor P fixed point by G. A0, A1 being finite dimensional algebras. So let's see how this works. So we want everything to be fixed points. So P itself, let's start with the first one, P itself. Well, if I tensor with C of G, take the fixed point by G, I'm getting P. That's a bit of a little trick here. Now the cross product, that's this. That's a matrix algebra over the group somehow. And this is in the group, tensor P by G. So we're done with the first one. The second one is, of course, by definition like this. Well, not exactly. At left, I do nothing. At right, fixed points by a subgroup, you can write it in this way using C of G over H as algebra, right? Now the Wassermann factor, we don't have to do anything, it's already in this form. And well, the diagonal subfactor is a bit more complicated because so far here G was finite, compact, so it was compact. Now I have a discrete group. So we'll use the dual of gamma, if you allow me, that's a compact quantum group. So we'll have to write down everything as fixed points under the action of G hat. And well, that's the way of doing it. I mean, some cross product, whatever, it's a bit more technical. So we're done with the remark that, for constructing such a subfactor, of course, you need the inclusion of high-dimensional algebras, G acting on P both A0 and A1, but G must be a quantum group because you see from the diagonal subfactors, we really need quantum groups here, we need duals. So in order to talk now about these subfactors in general, really covering all these, for examples, we need to talk about quantum groups. So here's your theory. There are so many theories of quantum groups. So here I just need something unifying compact groups and group duals. That's all. We won't get beyond that. So we'll find the simplest possible formalism unifying, let's see, so our compact groups, no assumptions here. Here we need them to be of matrix type, of Lie type, right? Having projective or unitary representations in general. So this must be Lie groups, and the discrete groups might be finitely generated. So I want to formalize unifying the compact Lie groups with the duals of finitely generated groups. And the minimal one, which is actually very beautiful precisely because it's minimal, is this one discovered by Voronovich some 30 years ago. So it takes star algebra with a unitary matrix with entries generate A, such that you have delta epsilon s of algebra maps if you want on generators like this. And the claim is that this can be written as C of G with G compact quantum group and C star of gamma discrete quantum group. So why is this claim true? So first I must construct examples here and here. So given a compact Lie group, that's your algebra. Uij are just the coordinates, they form a unitary matrix. And delta epsilon s are just the transposes of the multiplication unit inverse map of G. Let's see why this is true. So again, C of G with the coordinates, everything is satisfied. And this is, yeah, that's the formula of the multiplication coordinates, if you want, of the unit antipode. So inverse, the inverse. So you get C of G. So in general, now you can call A to be C of G with G compact quantum group. That's the idea. Now let's turn to group duals now. So they are finitely generated. So I take C star of gamma group algebra with the diagonal matrix formed by the entries G1, Gn. So let's see if this works. Of course, it's unitary entries generate. Because matrix is diagonal, this formula simply becomes delta Gi is Gi tensor Gi. So that's what's written here. It's actually a true finite group element. This, of course, exists. And same for coordinate and antipode. Coordinate is G goes to 1, antipode is G goes to G minus 1. So this is a formalism. It's a good one. Definitely you can do this. And G, of course, is gamma hat. Gamma is G hat and Pontryagin type duality. So now what does the theory say? We'll see, of course, there are many other examples, but this will come later. For the moment, we just needed this formalism unifying compact Lie groups with duals of finitely generated groups, and that's precisely what we have here because of these two examples. Now let's see what the theory says in general. So first you have a hard measure that's actually not trivial. It's resolved by Voronovich, who many people have looked for these kind of things, and Voronovich came with the answer in 87, yeah, 87, 88. So it's exactly as in the classical case, the statement. I mean, that's what you're looking for, a measure which is left and right invariant, an integration. And for constructing it, you start with the positive formula and you do this as our limit of convolutions. But proving that this converges and that it's independent of phi and everything, it's a bit technical, and that was proved by Voronovich after some efforts. Now, once you have this, you can develop a Peter-Weyl theory for representations. So The core representation of the Voronoi algebra, that's the correct terminology, is a matrix satisfying exactly the same conditions as U before. Okay, let's go back. You see, U, these are the conditions, the axioms. So I take exactly these three formulas, which correspond to the fundamental representation somehow. And here they are. I call such a matrix representation. And then you have Peter-Weyl, so it's semi-simple, irreducibles appear inside the tensor powers few k. As a co-algebra, you have this Peter-Weyl decomposition. It's orthogonal with respect to the hard measure, and also the characters form an orthogonal basis of, you can define as central. These are the elements which are invariant on the flip. So everything works just fine. In addition to this, you have other things like Tanaka, many other. But for what we need here, developing these fixed points of factors, that's all we need. Now let's go into fixed points of factors. So well, here they are. I mean, just in the quantum group, acting on P, on an inclusion. And we need minimality as before. A0 into A1 must be a so-called Markov inclusion. So this is actually automatically satisfied when A0 is C. So let's not get into that. It is true in general, let's say, for all the examples. G must be ergodic actually on both the centers. Once again, that's kind of trivial for all the examples. And you get our subfactor. So this is very standard. Now, yeah, the examples. So here they are, of course. They are all of this form. And you see on the left, usually we have C, what I was telling you. And on the right, usually we have Mn of C, 1, 2. So this is Mn of C, so it's ergodic. So yeah, John, let's not get into all the details, but there are some algebraic assumptions here which are usually satisfied. So have unified these four things. Now let's see how the theory goes. Well, the Jones tower, that's something that we talked about a bit last time, is obtained by taking the Jones tower for A0 to A1, extending, taking fixed points. The standard invariant, the idea is just P disappears, you know that, and also in the planar algebra. So let's see the proof here. Let's take a subfactor, Jones tower. What I was saying, it's enough to work out the basic construction. Then it's by Grant somehow. And now the whole point is that this is due to Weissermann. It's the invariance principle in the classical case, but can be extended by using these Peter-Weyl tools in the general case. That when computing the commutants, P just disappears. So you get the things here. So we're done. You see, I mean, that's exactly the so-called, these commutants form what Popper calls a lambda lattice, and part of them is, if you take I is 0, that's the planar algebra. Look at the results. Now, so what we have is a unifying theory, unifying this known for examples of subfactors of integer index, and we have these computations, Weissermann, planar algebra, everything. Now let's construct some new examples. Okay, that's where we wanted to get. So if you look at what we had there, we basically need actions of compact quantum groups on finite dimensional algebras. Now these algebras correspond to finite commutative spaces. So in the end, we need actions of quantum groups on finite spaces, non-commutative. So we need quantum permutations, okay, in a very general sense. Take any finite space X, which can be 1n or even non-commutative. We need quantum permutations of that, and then subgroups of these quantum permutations. So let's see first how the big groups work, the quantum permutations. So I take a finite non-commutative space coming from an algebra A, which by the way must be a direct sum of matrix algebra, the structure theorem. Then you can construct a quantum automorphism group in the following way. So start with n plus. This is the free unitary group. I mean, just take n times m matrix, which is biunitary. Both U and U transpose are unitaries. And the free algebra is somewhat generated by that. That's a quantum group. And then you just have to impose the condition which guarantees the existence of a coaction map with a little trick here discovered by Wang. So you won't get a universal object in this way. You have to assume that the canonical trace is invariant. Canonical trace is the one on A coming from the left regular representation. So that's somehow the counting measure in your space. And That's the subtlety here. If you take, let's just take A to BCN, so the space is 1n, underlying space. In the classical case, of course, there's a bigger quantum group acting on 1n, it's a symmetry group, right? In the quantum case is false. There's no biggest quantum group acting on 1n. You have to assume that the action leaves invariant the counting measure on 1n. It's a bit bizarre, but for things to work, that's what you need. So this is more or less due to Wang, and now, well, let's look at the fixed point subfactors with respect to these guys, which are the biggest. So in this way, we'll obtain the planar algebras, which are the smallest, like temporally Lieber versions of it. So if you take this subfactor, the very simplest one, you get temporally Lieb. That's a theorem, something that I proved long ago, I mean, 20-something years. And this applies, of course, to Sn plus and also to the quantum automorphism group of Mn. Mn is the non-commutative space corresponding to the matrix algebra Mn. And this is at the same time Qn plus, Qn plus. You can prove that. So you see, all these guys give temporally Lieb. I mean, there are somehow more quantum groups than subfactors in this, than fixed point subfactors in this setting. So I was telling you all the time, so you see quantum groups and subfactors. Of course, subfactors are somehow big and quantum groups are very small, but they're not inside subfactors. They are a bit, they are not exactly included because you see all these three guys give TLN. So there are problems there, projective leaves, things like that. So, okay. So anyway, get TLN now. Getting beyond that, let's try to construct Fus-Catalan now. That's the next level. And here you need to take a fibration somehow, I mean, a quotient of finite non-quantity spaces, and which corresponds to an inclusion if you have two finite dimensional star algebras, and you get Fus-Catalan. So that's once again something I did long ago. Now, so we have temporary Lieb, Fus-Catalan. Now, let's get one level up. So what can we do? So the interesting remark is that the Fus-Catalan construction, let's go back. So here in the vibrational finite spaces, I mean, it's a bit annoying. Best is to do it with spaces of type 1n if you want to understand. And here you're lead to these complex reflection groups, classical and free. So these are some organization of the hyperoctahedral group. So you're finding, which are quantum symmetry groups of the cube. So you're finally led to finite graphs. That's the next level after Fus-Catalan. And the theory here is that via this correspondence somehow between quantum groups and subfactors planar algebras, the planar algebra generated to an automorphism group finite graph is what Bish, Jones, and you call a planar algebra generated by a two box. And in that box, we have the Laplacian of the graph. So all this is very nice, and you can, there are of course many results here. I mean, all this work going on finite graph now in quantum groups. So many interesting things here to understand. So temporary Lieb is understood, Fus-Catalan too, and next level is finite graphs, and there's a lot of work going on there. Okay, so I'll be back to this also in the next lectures with more details, also a bit of analysis. See you soon.